Today, we're digging into one of the biggest paradoxes in quantum computing. It's this really tricky situation where the very thing that makes these machines so incredibly powerful might also be their greatest Achilles heel. So let's just start with this question. What if a quantum algorithm's amazing ability to search through millions of possible solutions is the very thing that makes it impossible to train? I know, it sounds crazy, but this is the catch-22 we're going to unpack right now.
Okay, so to really get this, we've got to look at how we actually train these quantum systems. Because on the surface, it's full of promise, but lurking just underneath is a massive fundamental challenge.
Right now, we're in what's called the NISQ era. That basically means our quantum computers are still a bit noisy, a little imperfect, so the most popular way to work with them is using something called a variational quantum algorithm, or VQA. You can think of it like a team effort. The quantum computer does all the heavy lifting, the quantum part, while a regular classical computer acts as a coach, constantly tweaking and training it to get closer and closer to the right answer. Now, if you want to solve a really tough problem, you need your algorithm to have what scientists call high expressibility. This just means it can explore a huge, complex landscape of possible answers. It has the power to look everywhere, leaving no stone unturned. Low expressibility, on the other hand, means it's stuck exploring a tiny little patch of that landscape, and it might completely miss the best solution. So obviously we want high expressibility, right? That's the whole point. Well, here is the twist. A few years back, some researchers discovered a really painful trade-off. They found that these super powerful, highly expressive algorithms create what are called flatter cost landscapes. And what that means, in plain English, is that the very feature that gives an algorithm its power also makes it almost impossible for us to train it. We can't guide it to the solution we're looking for.
And this problem has a name. And honestly, it's a perfect, if a little terrifying, metaphor for the whole situation. They call it being lost in the barren plateau.
Okay, so training an algorithm is kind of like walking down a mountain in a really thick fog. You can't see the bottom, but you can feel the slope of the ground beneath your feet. That's the gradient, and it tells you which way is down. A barren plateau is a landscape that's almost perfectly flat. The slope, your only guide, just disappears. It vanishes. So the classical computer, the coach, has absolutely no idea which direction to go. The whole process just grinds to a halt.
This image just nails it, doesn't it? Imagine you're dropped right in the middle of a massive, flat desert that goes on for miles in every direction, and someone says, "Okay, find the lowest point. Good luck." You have no hills, no valleys, no slopes to guide you. You're completely and utterly lost. And that is exactly what it's like for a quantum algorithm stuck on a barren plateau. So, are we stuck? Is this the end of the road? Absolutely not. This is where things get really clever. Because physicists and computer scientists are now coming up with all sorts of ingenious ways to navigate this terrain and, well, escape the desert. And some of these escape routes are starting to show real promise. For instance, instead of using really deep and complex quantum circuits, we can use shallower ones. Or we can link the algorithm's settings, its parameters, so they don't all just run wild independently. We can even give the algorithm a head start by initializing it close to a solution we already think is pretty good. See the pattern here? It's all about carefully reducing that expressibility just enough to carve some hills and valleys into the landscape, but without making the algorithm too weak to solve the problem. Let's just zoom in on that idea of correlating parameters for a second. Think of a quantum algorithm as having this giant control panel with millions of tiny little knobs you can tune. If you try to tune every single one independently, you get that flat, featureless, barren plateau. But if you link them together, correlate them, now you're not turning millions of knobs anymore. You're just turning a few master knobs that control big groups of the others. And that, right there, dramatically simplifies the search and helps create a path you can actually follow. But here's a thought. What if just tweaking the algorithm isn't enough? What if the problem is more fundamental? What if the very map we're using to navigate is wrong? This has led some researchers to a radical conclusion. We need to invent entirely new kinds of math for these new quantum worlds. Think about it like this. If you have a flat paper map, the shortest way to get from New York to London is a straight line. Simple. That's standard high school Euclidean geometry. But we all know the Earth isn't flat, right? It's a globe. It's a curved space. On a globe, that straight line from the map is actually a big, inefficient curve. The true shortest path is what pilots fly, a great circle route. And to find that, you need a totally different kind of math, one designed for curves called Riemannian geometry. And here is the big aha moment.
These optimization landscapes in quantum mechanics, they are not flat. They are inherently curved, weird, high-dimensional spaces. So trying to solve them with our standard flat map math is why we get lost. It's the wrong tool for the job. So what are researchers doing? They're building brand new toolkits based on this geometry of curved spaces. And one of the first, a real game changer, is a library called QAGO.
And this is not just some abstract theory on a whiteboard. Nope, QGOpt is real code. It's a software library that people are writing and using right now. You can think of it as a specialized GPS for quantum algorithms. It gives them the mathematical tools of Riemannian geometry so they can find the true shortest path to the answer, even when the terrain is incredibly strange and curved.
So where is this all going? Well, when you start combining these smarter algorithm designs with these powerful new mathematical maps, we're finally starting to see a real, practical path forward for training these quantum computers.
And the best part is, it actually works. This graph right here, this is what success looks like. You see those lines trending downwards? That's the algorithm getting closer and closer to the correct answer. It's converging. By using these geometrically aware tools like QGOpt, the algorithm is finally able to navigate the landscape, escape that barren plateau, and find the lowest point we were looking for all along.
All of this leaves us with a really fascinating final thought, doesn't it? As we race to build bigger, better, more powerful quantum computers, it makes you wonder, maybe the ultimate key to unlocking quantum advantage won't just be the hardware itself. Maybe it'll be the cleverness of the mathematical maps we design to navigate their beautiful and complex new worlds.